Section 1.2 is a continuation of Section 1.1 as we continue to talk about functions and their graphs. So the simplest type of function and the function we learn about first in algebra are linear functions, right? They're called linear functions because the graph of them forms a line, okay? These functions are of the form f of x equals mx plus b, where m is our slope and b is our y-intercept, okay? The domain of all linear functions is all real numbers unless otherwise specified. They can have slope that is negative, which means they'll look like a decreasing function, positive, which makes them look like an increasing function, or 0. Okay, this has 0 slope, and this is what we call a constant function. These are going to look like f of x equals 4, or otherwise known as y equals 4. The domains of vertical lines are a little bit different. So vertical lines are defined as x equals c, where c is any real number, and they have undefined slope, okay? It's also important to note that these are not functions. They're not functions because they fail the vertical line test. So if I was to graph x equals 2, that's the line where at every single point x equals 2. So here's where, negative 2. So here's where x equals negative 2. So it doesn't matter what y is. My y could be 1, my y could be 6, my y could be negative 6. The graph of x equals negative 2 is a vertical line. And it is not a function because, as you can see, it would fail the vertical line test because every single point is on this line. So how do we calculate the slope? So we determine the slope in our line to be the ratio of change in y, so that's our rise, how much we go up or down, over our change in x, which is our run. Okay, that's our horizontal change. So you're probably going to hear me say something like rise over run. Rise just means I'm talking about going up or down. Run means I'm talking about going left to right. So we have this formula for slope, which is our vertical change, which would be our y2 minus our y1, over our horizontal change, which is our x2 minus our x1. So why don't we go ahead and calculate the slope that passes through the points 2, negative 4, and 6, negative 3. Now, quick note, sidebar, it doesn't matter which points are your x1, y1, or x2, y2. Regardless of whether you do it either way, you're going to get the exact same slope, which is so nice that math works out that beautifully. So if I have slope, that's going to be m equals, I'm going to label this point x1, y1, and this point x2, y2. So my slope is my change in y, so I have negative 3 minus negative 4 over my change in x, which is 6 minus 2. That gives me a slope of negative 3 plus 4 over 6 minus 2, which is 4. Remember, two negatives make a positive. So I have positive 1 over 4. So my slope is 1/4 in this case. Remember, slope can be negative, slope can be positive, it can be fractions, it can be 0, it can be undefined. So if we don't know our y-intercept, we can't put our slope, our equation in y equals mx plus b form, right? This is called point-slope form. It's the best, this is called slope-intercept form. It's a great form because then from looking at our equation, we'll know how to graph it. But if I do know my slope and a point, or we need to know 2 points on our line, we can find the equation using this formula right here, which is supposed to be f of x, which is y, right? Y minus y1 equals m times x minus x1. So let's go ahead and use our point slope form and solve an example and graph the line. So if I have my equation, y minus y1 equals m of x minus x1, remember that y equals f of x. Like f of x is just denoting that we know it's a function. But you'll most commonly see it with a y instead of an f of x. So I have my slope to be negative 3, so I'm going to substitute that in. I know my x sub 1 is negative 2. Notice how, because it's a negative 2 and it's a minus, I went ahead and put that in parentheses so we don't forget to change our sign. And then I have y minus y1, which is 7. So y minus 7 equals negative 3 times x plus 2. So let me go ahead and distribute that 3. That gives me negative 3x minus 6. I'm going to go ahead and add 7 to both sides. So I get y equals negative 3x plus 1. So let's go ahead and graph this. Now I know my slope is negative 3, and I know my y-intercept is 1. So here we can go ahead and plot our y-intercept. I have my y-axis right here, and my y-intercept is a positive 1. And my slope is negative 3. Remember that slope is the change in y over the change in x. It's rise over run. Well, what's my run in this case? What I like to think about is how could I write negative 3 as a fraction? If I wrote negative 3 as a fraction, I have a denominator of 1. Remember that any number divisible by 1 is just itself. So my slope is negative 3, so I'm going to go down 3. And my run is 1, so I'm going to go over 1. And remember, you only need 2 points to graph a line. But let's fill in some extras. So here we have the graph of our line, y equals negative 3x plus 1. Now, a linear equation is a special type of a more generalized class of functions, and those are called polynomials. Okay? A polynomial function is any function that can be written in the form that looks like this. Now, this is a lot going on. What is this saying? This is saying that if I have a variable raised to any degree, and I have constants, and I have other variables raised to a lesser degree, and I have a sub 0, this is just a constant, right? And these are our coefficients. Then this is a polynomial, and right off the bat, it's a function. I don't have to check that. Okay? So we say that n is the degree of our polynomial, where n is the largest exponent on our variable. Let me write that down. That's another good way to put it. N is the largest exponent on our variable. Very cool. So, a degree 2 polynomial has the form f of x equals ax squared plus bx plus c. These are also called quadratic equations. Oh, I forgot how to spell it for a second. Quadratic equations. And what's important about quadratic equations is the shape is always going to be a parabola. So the simplest parabola we could have is f of x equals x squared. Its leading coefficient is 1. Its degree is 2. That's what makes it its graph a parabola. And what it does is it squares each value of x. And because when we square negative values, they become positive, it's important to note that my domain here is negative infinity to infinity. And my range is just from 0, but 0 is included, so I do a square bracket, all the way to positive infinity. So here's a quadratic function. The next type of function is a cubic function. It's a degree 3 equation. Sorry, a degree 3 polynomial. It's a function because it passes the vertical line test, and its domain and range are both negative infinity to positive infinity. This is because if I was to cube a negative number, like negative 3 cubed, I'm going to get a negative number back because 2 negatives make a positive, but that third negative makes it negative again. So here's a cubic function, which is another example of a polynomial. Some polynomials are power functions, okay? And a power function is any function of the form a x to the b, where a and b are any real numbers, okay, so they just have to be real numbers on the number line, and our exponent is a positive integer, okay? And we write these as f of x equals a x sub n. It's important to note that if I have n even, my function is going to be even, right? That means it's symmetric around our y-axis. If n is odd, that means my function is going to be symmetric around the origin. And if you don't remember that, feel free to go back and watch the videos from section 1.1. And I can prove something is even or odd by solving f of negative x. So let us solve this, okay, by solving f of negative x. So let's say that n is even. If I have f of negative x equals a, negative x to the n, well, any even combination of numbers, right, that's going to have my negative x, my negatives cancel out. I don't have that one regular negative left over. So I have f of negative x equal a x to the n. This is the same as f of x, which means this function is even. So n is even and our function is even. It's nice to make that distinction because I'm using the word even to have multiple meanings in this case. Now if n is odd, right, that means it's some number where mod 2, it has a remainder of 1. And every odd number if I take a to the negative x to the n and n is odd, I'm going to end up having a negative left over. So I have negative a x to the n. So this means my function is odd.